Good day, I'm J Wildberger, and today we're going to be looking at canonical forms for logic circuits. What we want to do is we want to be able to take a circuit, something like this, and find an algebraic representation of it that contains the essential information about what it does with respect to inputs and outputs. And we want to do this in two different ways to compare them. First of all, with the Algebra of Boole, which I'm trying to persuade you is actually primary and far superior for circuit analysis, and with the more traditional classical Boolean algebra that's currently taught in engineering courses all around the world. I'm trying to get us to think about moving from this scenario to this more advanced, more powerful, ultimately simpler framework. Okay, so for example, here is a circuit consisting of some elementary logic gates. There's a NAND, there's an AND, there's an OR. We have two inputs, A and B, and these gates do something to these inputs and give us an output C. And we've analyzed this, and we've analyzed it both through both of these frameworks, and we've seen that in the Algebra of Boole situation, it can be reduced to the expression A plus B. So this output is just the sum in the Algebra of Boole, so that's like sum mod 2 of A and B. While in the Boolean algebra, more traditional point of view, it's a little bit more complicated. It's really an XOR gate, but this XOR gate is represented either by the expression A B bar circle sum A bar B, or by A circle sum B times A bar circle sum B bar. These are kind of equivalent, symmetrically different, but dual kinds of ways of expressing this. But the basic idea is that we've got this complicated, possibly rather big circuit in there involving all kinds of gates, and we want to find canonical forms of representing it, like this, okay, algebraic forms that dispense with the detail, that don't tell you what the detail is. In fact, the detail is lost, but just tell you effectively what this combination of gates does with respect to inputs and outputs. Well, for us, typically only one output. Okay, that's what we want to do today. So a good place to start is the situation where we have two inputs, say A and B. And we've already talked about there being basically 16 connectives or operations that we can do with these two inputs. And I want to have a look at that again, but now both from the Algebra of Boole and the Boolean algebra point of view. So let's start with the even one. So there's 8 even connectives or operations, and here they are. And what we see is the inputs A and B. So we're running through all the 4 possible ways of assigning zeros and ones to them. And then here is the sum, here is the product, here is A plus AB, and then B plus AB, and A plus B plus AB. Now, underneath, I've also given you the Boolean algebra expressions for the same connectives. So with the Boolean algebra, we still have the product, just like this, but we also have this negation, and we have a circle sum, an inclusive OR, as opposed to this ordinary plus, which is really like an exclusive OR. And we've just seen that this XOR gate then is described in either of these two fashions using the Boolean setup. And AB, well, that's the same. This thing here is A times B bar, and this one is A bar times B, and this is A circle sum B. This is the usual inclusive OR operation on the inputs. Okay, so these are kind of examples of canonical forms. So if we're interested in a gate which produces these outputs for these inputs, then the Algebra of Boole expression and the Boolean algebra expression or canonical form would be the same. But if we're looking at this one here, then the way the Algebra of Boole describes this, the way the Boolean algebra describes it, are different. And the difference is most notable at this one here, where here there's an A plus B, and here there are these two expressions. Now here are the other 8 connectives or operations. We've called them the odd ones previously. So here they are. The A and B are no longer visible, but here is the inverse of A, and here's the inverse of B. In the algebra of Boole, the inverse is obtained by adding 1. So one way of thinking about this is just to add 1 to all the previous ones. In other words, to invert each column. Replace all the zeros with ones and the ones with zeros. And then here are the corresponding Boolean algebra names for the same thing. Now we get some circle sums appearing, and over here then there's a product. And maybe over here, this is the negation of the XOR gate, sometimes denoted XNOR, the XNOR gate. Okay, so 1 plus A plus B in the algebra of Boole, and AB circle sum A bar B bar, or A circle sum B bar times A bar circle sum B in the Boolean algebra story. Okay, so these 16 exhaust all the possibilities for circuits which take two inputs A and B. Okay, so you have any circuit, combination of gates, no matter how complicated it is, if it has just inputs A and B, then effectively it's going to be one of these 16 operations. Okay, so but now we can kind of think about generalizing that, because we can think about what happens if we have more than two inputs. Then we get something that maybe shouldn't be called operations anymore, or connectives. They're just sort of functions of inputs. Okay, and they play a big role in circuit analysis. So we just want to shift our orientation just a little bit with respect to these 16 connectives or operations. So they can also be regarded as Boolean functions. These are functions from B2 squared to B2, where B2, 0, 1 is our standard bifield. It's the basic arithmetical framework that everything is built on. And here is B2 squared, which is the space of two tuples of bifield objects. So B1, B2, ordered pairs where the BI's are either 0 or 1. This is a two-dimensional Boole algebra. Okay, and we can think about a Boolean function as being a function that takes these things and gives us elements in the bifield. So for example, if we write out A and B, here are the four possibilities, and we choose one of the functions, say A plus AB, okay, that has value 0, 0, 1, 0. So we can think about that now as being a function on B2 squared. B2 squared is a set of ordered pairs, 0, 0, 1, 0, 0, 1, and 1, 1. And these ordered pairs form a little square there. Okay, it's like a two-dimensional square. And the vectors are just over here. Here's 0, 0, here's 0, 1, here's 1, 0, here's 1, 1. And these values are telling us the function's values at these vertices. So the value at 0, 0 is 0. The value at 0, 1 is 0. There's 0, 1. There's the value of 0. The vector 1, 0 has associated to it a value of 1. There it is there. And the vector 1, 1 has associated to it a value of 0. So geometrically, what a Boolean function is an assignment of zeros and ones to the vertices in this square. More generally, cube or hypercube or something like that. And here is the both the Algebra of Boole expression for this function, like sort of the canonical form for it. And here is the Boolean algebra canonical form for it, A times B bar. Okay, so what we want to do is we want to take this and kind of generalize it, extend it. So a Boolean function more generally is a function from B2 to the n to B2 for n equals 1, 2, 3, or possibly higher values. And this n here, we call it the dimension of f. The dimension of f. In the literature, sometimes the word arity is used, but dimension is sort of simpler, I reckon. Okay, so let's look at actually an even more simple case, the case when n equals 1. So dimension 1. In that case, a Boolean function is just a function from B2 to B2. So there are then exactly 4 Boolean functions of this dimension. And here they are. Okay, so now we only have one element in our vector, in our input vector. So it's basically one input, say A. And this input can only have the values 0 or 1. So the question is, what are the possible functions on 0 and 1? Well, one function is 0, 0. Another is 0, 1. Another is 1, 1. And another was 1, 0. And the names for these are, in the algebra of Boole, this is the 0 function. This is the 1 function. This is the A function. In other words, it has the same values as the input. And this is 1 plus A, which is the way we express negation in the algebra of Boole. In the Boolean algebra framework, the names for these 4 Boolean functions would be 0, A, 1, and A bar. Right? In the Boolean algebra, we have the bar. In the algebra of Boole, we don't have the bar, but we are able to add 1. So exactly 4 Boolean functions. And okay, it's simple, but still it's an interesting case. So any logic gate that we build with only one input A will give us one of these 4 Boolean functions. So to illustrate that, let's consider this gate, okay, which contains the basic gates. Well, here's a NAND gate, here's an AND gate, and here's an XOR gate. And here's our input A. So the input A is arriving here, and then it's being forked over there. It's also going through this inverter. It's like a NOT operation, and it's also coming directly there to that input. So let's have a look at what the output, say X, is as a function of A. So the 2 values are 0 and 1. So let's ask ourselves, what happens if we set A equal to 0? So there's 0 coming in along A here. So this NAND gate, well, there'll be 0, 0. So I remind you, the NAND is like the negation of the AND. 0 and 0 is 0. So if we negate that, we're going to have 1 up here. Okay, so keep in mind, there's 1 up there. And what about down here? So 0 coming in here, that's going to be inverted here, and going to have an input of 1 at the top here, while the bottom one here is going to be a 0. So there's a 1 and a 0. And we do an exclusive OR on that. Exclusive OR. So 1 or 0 is 1. Okay, so we have a 1 coming in here. So we have 1 on the top and 1 at the bottom. And this is an AND. 1 and 1 is 1. So the output is 1 if the input is 0. And what if the input is 1? Okay, so we have 1 coming in here. So then there's a 1 and the 1. The 1 and the 1, this is a NAND gate. So if we take the AND of 1 and 1, we get 1. We negate that, we get 0. So now there's 0 coming in there. Okay, what about here? We've got 1 coming through here, so it'll be a 0 coming in there and a 1 coming in there. Still a 0 and 1, and this is an XOR, so we'll still have 1 coming through here. So what did we say? We had 0 coming in at the top, and now we have 1 coming in the bottom, and this is an AND. Okay, this is an AND. So 0 and 1, that's 0. Output of 0. Let's look at this from a canonical form point of view. So if we want to write an expression for it, let's write this like this. So f of A. And I'm going to use a Algebra of Boole calculation because that's what I'm trying to get you towards. So let's have a look at how we would write this expression out. So we've got 2 things happening. There's an AND here. Okay, there's an AND. AND is like multiplication. And what are we ANDing? Well, we're ANDing this thing here. This is a NAND. What is a NAND in the Algebra of Boole? Well, it's a 1 plus the product. So 1 plus A times A. That is the NAND, the effect of this NAND gate. And we have to multiply that, because this is an AND, we have to multiply that by the output of this XOR gate. So what's happening to this XOR gate? So this is an XOR gate. XOR is just addition in the Algebra of Boole. Okay? So what are the 2 inputs here? Well, this is an inverter, so we have the inverse of A, which is 1 plus A. There it is. That's the input there. And here the input is A. So we have to add A. Okay, so what is all of this? Well, 1 plus a times a is a in the algebra of Boole. So this is 1 plus a. And, okay, product. And we have to multiply it by, here is 1 plus a, but a plus a is always 0. So we are just really multiplying by 1. So we get 1 plus a. That is indeed what we got over here. This is basically an inverter. Takes the input and inverts it. So it's really operationally the same as this thing here. Okay? And the canonical form for it dispenses with the details and just gives you effectively a way of seeing what this is in terms of what happens to the inputs to create the outputs. Okay, this is a very simple situation because we only have one input A. But now we want to understand this situation in more complicated fashions where there's more than just one or two inputs. Okay, so let's go to 3 dimensions. So now we're considering Boolean functions which take b2 cubed to b2. Now, how can we understand that? Well, so here are our 3 inputs. They're going to be A, B, and C. And now there's 8 different possible ways of assigning zeros and ones to these 3 inputs. So there's 2 ways, times 2 ways, times 2 ways. So 8 ways altogether. And we can list them conveniently by just essentially writing the numbers from 0 to 7 in binary. That's 0, 1, 2, 3, 4, 5, 6, 7. It's a systematic, canonical way of orienting or organizing those 8 possible values that our 3 inputs can have. Now, what is a Boolean function? A Boolean function is something that takes one of these rows and outputs either a 0 or a 1. So the rows here are like triples of zeros and ones. So that's our b2 cubed. So that's an element of b2 cubed. That's an element of b2 cubed. And altogether the 8 elements of b2 cubed form, well, a cube. Okay. So here is another picture of these 8 things. There is 0, 0, 0. That's like the first one. 0, 0, 1, 0, 1, 0, 0, 1, 1. Where's 0, 1, 1? Oh yeah, 0, 1, 1, here we are, yes. 1, 0, 0, there. 1, 0, 1, there. 1, 1, 0, there. And 1, 1, 1, there. Okay. Now, what we're doing when we're creating a Boolean function is we're assigning a 0 or a 1 to each one of those vertices. Like this, okay? So this is an example of a Boolean function in this dimension. It's called f. It has the values 1, 0, 0, 1, 0, 0, 1, 0. So this is 1 out of how many possibilities? 256. Because there's 2 times 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 2. There's 2 to the 8 different ways of assigning zeros and ones to these 8 positions. Now this one, we can think of it geometrically as actually assigning zeros and ones to these vertices. So 0, 0, 0 gets the value 1. 0, 0, 1 gets the value 0. 0, 1, 0 gets the value 0. Where is 0, 1, 0? There's 0, 1, 0. Put a 0 there. 0, 1, 1. It's up here. It gets the value 1. 1, 0, 0 gets the value 0. 1, 0, 1 gets the value 0. 1, 0, 1. There we are. And 1, 1, 0 gets a 1. 1, 1, 0. That gets a 1. And 1, 1, 1 gets a 0. Okay, so this particular function f is an assignment of zeros and ones to the vertices of this cube. And that's how I want you to think about it. Okay, I want you to think about this as being a geometrical assignment of numbers from the bifield to the vertices of this cube. And there's 256 ways of doing that. This is one of them. Okay. Now, the connection with circuits. Well, this thing could well be the result of a circuit that we build. We build a big logic gate circuit with inputs A, B, and C. And there's all kinds of NAND, NOR, XORs, ANDs, negators, whatever. Okay, and then finally there's an output. And the combination of gates is such that when we put in these various inputs, the outputs are as determined here in this column. Okay, so this is the form or the realization of a circuit gate where we've dispensed with the detail of what actually the circuit consists of in terms of individual gates, but just looking at the effect, what it does to the inputs to give you an output. So to put it another way, if you have 3 inputs, there are essentially 256 inequivalent circuit or gates that you could build. 256, no more, no less. Any combination of gates with 3 inputs is going to be one of those 256 different possible outputs. And now we come to a very natural question. How do we express this Boolean function f? Algebraically, instead of listing all the values, is there some more succinct, canonical way of expressing it algebraically? So here is the function f. Again, I've just copied it here. Here are the 8 different possible values of the inputs, A, B, and C, and here's the values corresponding of f. And we want to express this thing algebraically. And there's a simple way of doing this. Actually, there's 2 simple ways of doing this. Okay, so the first one is the following. What we do is we concentrate on the places where the function has the value 1. There are 3 such places in this case here. And we just look at these rows. Okay, we look at these rows. I'm going to start with the Boolean algebra point of view. So this is the standard story that you find in engineering courses. So what do? Well, you look at each one of these rows, and each one of these rows is going to contribute a term in a sum. That term is going to be a product. It's going to be a product of either the inputs or possibly their negations or bars. So here we see 0, 0, 0. And this is telling us that this value of 1 occurs precisely when A is off, B is off, C is off. When A, B, and C are all 0. And we express that by writing A bar, B bar, C bar. Okay? A is off, that's the bar. B is off, that's the bar. C is off, that's the bar. That will result in a 1 if A, B, and C are all 0. And will otherwise result in a 0. So the only way this product can be 1 is if each of the constituents are 1. That's the nature of the AND operation. An AND is most of the time 0. It's only 1 when each of the individual products are in themselves 1. Okay? So the only way to make this thing 1 is to make sure that each of the ingredients are 1, which is effectively saying that A, B, and C both have to be 0. So that captures this first possible 1 that we're getting there. And then the next one here, well, that's described by A bar B C, because there's a 0 in the A place and a 1 in the B and C places. Otherwise, the argument's the same. This will be 1 precisely when A is 0, B is 1, and C is 1. And then the next one down here, we get an A, B, C bar. This will be 1 precisely when A is 1, B is 1, and C is 0. And we take a circle sum because the way we can get a 1 is either this way, or this way, or this way. So this is a Boolean algebra expression for this Boolean function f. So it's like a canonical form. But you might ask, wait a minute, but there are all these ways of simplifying Boolean expressions. How do we know that this thing doesn't simplify and give us a more concise Boolean expression? That's a very good question. That's a very good question. And it turns out that in this case it doesn't simplify, so this is as good as it gets, but that's just because of this particular example. Okay, so there's a question here about in general, how do you know whether what you get here is as simple as possible or not? We'll have to talk about that a little bit later. Okay, now the Algebra of Boole story. It's the same kind of thing. We're still looking at each one of these rows, but we describe them differently using the Algebra of Boole notation. So instead of A bar, B bar, C bar, we write 1 plus A, 1 plus B, 1 plus C. So this will be 1 when A, B, and C are all 0. And otherwise, it's going to be 0. So this is exactly the same as that thing. And then we're going to take a sum. So we're going to this, or this, or this. And you might say, what's the difference? Well, here there's a circle sum, here there's a sum. Because these are all distinct. There's no way that one of these can be 1 and the other one can be 1 as well, right? If this one's 1, then this one's not going to be 1. This one's not going to be 1. So with this kind of situation, it doesn't actually matter whether there's a circle sum or a sum. The effect is the same. So our next row over here is described by a 1 plus A, B, and C. And the third row by A, B, and 1 plus C. Okay, but now we're working the Algebra of Boole, which is just like ordinary algebra with polynomials, except that it's a little bit simpler because we have these mod 2 reductions that we can do whenever we can. Okay, but we just start by expanding. So we'd have to expand this thing out. Okay, so what do we get? We get 1. So if you expand this thing out, you get 1 plus A plus B plus C. And the quadratic terms AB, BC, AC, and that will be the cubic term ABC. So there's altogether going to be 2 times 2 times 2. That's 8 possible terms. 1, 2, 3, 4, 5, 6, 7, 8. Those are all the 8 terms that you get by expanding that first thing. And then here we get BC plus ABC. You get those 2 terms. And here you get AB plus ABC. Okay, but now this is the Algebra of Boole. So in this case, we need to remind ourselves that whenever you have 2 of anything, that's the same as 0. So if we start listing the things that we have a 1, we have A plus B plus C. What about AB? Well, there's an AB there. Oh, but there's an AB there as well. So there's 2 of them, so it disappear. What about BC? Do we have any more? Oh, there's another BC. There's 2 BCs. They disappear. What about AC? Well, there's only 1 of them, so it stays. And the last terms are the ABC. There's 1 there, there's 1 there, there's 1 there. So altogether there are 3 ABCs, but 3 times ABC is the same as 1 times ABC, because 2 times ABC is 0. So we just get plus ABC. So this is then a polynomial expression in the A, B's, and C's that is the canonical form in the Algebra of Boole for this Boolean function. And this is really a canonical form. It's got a solid red thing over it. This is beautiful. Okay, it's a polynomial. In fact, all of the terms, none of them appear with higher powers, because if there were higher powers, we'd always reduce. But so it's not going to happen. But it's a canonical algebraic capturing of this particular Boolean function. But there's actually another way of proceeding as well. Okay, so there's an inverse approach to the same question. So I've repeated the data here, A, B, C, and the values of f, 1, 0, 0, 1, 0, 0, 1, 0. And now what we want to do is we want to look at the rows that have 0 values for f rather than 1. So there's 5 of them, that row, that row, that row, that row, and that row. And we can also analyze this Boolean function by looking at those rows. Okay, so how can we do that? Well, so if we start with the Boolean algebra story, this function is determined by the fact that it has these values of zeros exactly at these spots. So when is this thing 0? This thing is 0 when, well, this thing here, when A is 0, B is 0, and C is 1. That's represented by this, A bar, B bar, C. When this thing is on, when all of these conditions are met, then this is going to be 1. And And then we're going to have an output of 1. So to get an output of 0, we need to take a bar of this. So you see there's a big bar over the whole thing, okay? Because we're talking about 0 values now, so we have to put a bar. Okay, so we've got this element here for this row here, and then A bar, B, C bar expresses this row. A, down here, A, B bar, C bar expresses that row. A, B bar, C, that row, and finally the last one, A, B, C. Okay. So if any one of these conditions are satisfied, then the corresponding element here will be 1. The rest will be 0. Inside the bracket there will be a 1, and when we take the bar, we're going to get a 0. That will then correspond to exactly the places where this thing is 0. Now, this is a little bit complicated looking, and this bar on top is not very nice. So we can replace this with another expression using the De Morgan law. Okay? So if we have a sum of things and we take the bar of that, that's the same as the product of the individual bars of things. So we could just take the product, and here are a bunch of products, of the bars of these various things. So what is the bar of something like this? Well, the other De Morgan law tells us that the bar of a product is the sum, circle sum, of the corresponding bars. So if we take the bars of this thing here, we're going to get A, circle sum B, circle sum C bar. Okay, so we've inverted each one of these. A bar goes to A, B bar goes to B, C goes to C bar, and we've taken the circle sum of them. And we get a product term, one of 5 similar products, one for each one of these terms. So this is some kind of canonical form. But it's quite complicated, and it has a lot of operations in it. And we suspect that it's probably not the optimal one. In fact, the one that we got on the previous page was definitely shorter. So we don't want this to be a canonical form. So there's some kind of reduction that possibly we could do here, but that would involve us, utilizing our understanding of Boolean algebra to simplify it. Now that can be done, but I just want to point out that this doesn't really constitute at this stage a canonical form that's particularly convincing. It looks like more work needs to be done to get something that's really canonical. On the contrary, let's look at the Algebra of Boole story, where we basically do the same kind of calculation, but everything in the Algebra of Boole. So instead of having A bar, B bar, C, we have 1 plus A, 1 plus B, C. There's the corresponding term there, 1 plus A, B, 1 plus C, and then here A, 1 plus B, 1 plus C, A, 1 plus B, C, and A, B, C. So we have all of that, and then we have to negate the whole thing. But in the Algebra of Boole, negating just is adding 1 to it, so that we're adding 1 at the end. Okay, so now we simplify. How do we simplify? We just expand everything out. Okay, so we expand the first term, we get a C, an AC, a BC, and an ABC up to there. Then we add these ones. We get a B, an AB, a CB, and an ABC. Here we get an A, an AB, an AC, and an A plus ABC. And here we get an AC plus ABC or ACB. And here is just a single ACB. We still have to remember to add 1 at the end. Okay, does it simplify? Yes, it simplifies to this. So there's a 1. A, B, and C, those are the only linear terms that appear. The quadratic terms, AC, how many times does AC occur? There's another one. There's a third one. So there's 3 of them, so we get an AC. How about BC? Occurs once there, BC, BC, BC. That's only 2 of them, so it disappears. What's the other one? AC. AC is where? There's an AC there, and there's an AC there. There's only 2 of them, so we've already done AC. So the other one was AC, BC, and AB, sorry. Okay, AB, where is that? There it is, an AB, and there's another second AB. There's only 2 ABs, so there's no ABs either. And finally, ABCs, there's 1 there, that's 2, 3, 4, 5. There's 5 ABCs, and that simplifies to a single AC BC. So we get 1 plus A plus B plus C plus AC plus ABC. Not entirely surprisingly, we get exactly the same thing as we did in the previous method. Okay, so we're getting the same canonical form. It really is a canonical form in the Algebra of Boole story. Now, why are these two methods both useful? Well, because you can sort of see that if you had lots and lots of inputs, so this column would be very, very long, to work with this, if your Boolean function had just a few ones, then you would want to concentrate on those ones, and you'd use the technique on the previous slide. On the other hand, if it was mostly ones and only a few zeros, then you would want to look at it from this inverse point of view, just concentrate on the places where it's zero. So both of these techniques are in fact quite useful. It's just that in the Algebra of Boole situation, they give you always the same thing. But with the Boolean algebra, typically you don't get the same thing. You get one, which is sort of like a sum of products, or the other way you get a product of sums. So we'll have to talk more about that, but it's really this sort of dichotomy of canonical expressions that occurs at the Boolean algebra level that we don't see with the far superior Algebra of Boole. Okay, so this is great. We're getting a handle on this, but clearly we need to think a little bit more about these possible outputs, especially in the Algebra of Boole. What kinds of expressions are we able to get there? And we're connecting then very naturally with just ordinary polynomial arithmetic or algebra at a high school level, even simplified because of the wonderful mod 2 reductions. So it really becomes very, very simple algebra, and we're going to explain that and give some nice examples next time. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.